Good morning, sir. Dr. P.S. Patnagar, am I audible to you?
गुड मॉर्निंग डॉक्टर भटनागर, कैसे हैं आप?
हमें लग रहा है सुधीर जी की मूंछों से जब डर गए।
Sir, are we audible? We cannot hear you.
वो वो पता लगा वो पता लगा अरे अमर
इसमें एक व्हाइट लाइट जलनी थी ना, वो क्यों नहीं जल रही?
सर आवाज नहीं जा रही है हमारी।
हाँ, हमारी आवाज तो ये आप कैन यू हियर मी नाउ?
Yes, sir. Very good morning.
Yes,
ओके,
sir.
वेरी गुड मॉर्निंग। यू कैन हियर मी नाउ? हेलो। अभी अरे हाँ, ये तो मैडम का है। आधा दिखता है, आधा नहीं। और नीचे ठीक है, ठीक है, ठीक है, वो लिख रहे हैं।
Good morning, Dr. Neetu.
Yeah, very good morning.
Hello, Dr. Bhatnagar.
Hello, how are you, madam?
I'm good. How are you, sir?
I'm fine, thank you. We are waiting for the
Okay. All right.
from IT Kanpur.
Oh, okay. Okay.
Actually, Dr. first is yours, so I think we can start. Meanwhile, Dr. Komadi from IIT Kanpur will join us because my lecture is jointly with her.
I see. So, before us,
Yes. Yeah, we can start meanwhile. Meanwhile, we can start.
okay. But
Uh,
there are some. Uh,
yes, ma'am.
no, actually, I thought. Yeah, sure. Please go ahead.
Okay. Dr. Sushma, shall I start the webinar?
Yes, Aradhana. Please go
Okay.
ahead.
Yes, ma'am. Good morning and a very warm welcome to the webinar on COVID-19, Some Insights, organized by National Institute of Disaster Management, New Delhi. Firstly, I would like to welcome my Executive Director, Major General Manoj Kumar Bindal, to this webinar. I would also like to welcome our esteemed speakers for the session. We have Dr. Neetu Kumari, Associate Professor, Mathematics Department, IIT Mandi. Dr. Kumudi Patil, Assistant Professor, School of Humanities and Social Science, IIT Kanpur, and Dr. P.S. Bhatnagar, Scientist E and Officer in Charge, Western Regional Center, Zoological Survey of India, Pune. I welcome all the esteemed speakers to this webinar. And lastly, I would also like to welcome all the delegates, professional, academicians, faculties, and students from multidisciplinary background who have joined on this webinar with us. I welcome you all. Moving ahead with the session, the keynote was supposed to be addressed by our executive director, but unfortunately, due to work obligation, he was not able to join the webinar. Before we start with the presentation, I would like to highlight few objectives of the webinar. The objective of the webinar is to understand the devastating effect on global health with reference to COVID-19 pandemic, to reflect on history of epidemics and pandemic. This webinar also provides an overview on mathematical model and prediction of COVID-19. What lessons can be learned from existing health approach, from experience in emergencies or health crisis? A case study of India, Brazil, Russia, and Peru will be presented. What are the emerging current and solution response to COVID? Uh, to promote global, regional, national advocacy for COVID-19 preparedness and best practices across all sectors. And lastly, to advocate the multi-sectoral coordination for COVID preparedness response and recovery using the all-hazard disaster risk management approach. Now, moving ahead with the session, we have with us Dr. Neetu Kumari, Associate Professor, Mathematics Department, IIT Mandi. Dr. Neetu Kumari is renowned expert in the field of nonlinear dynamics and presently is working as Associate Professor in the Department of Mathematics, IIT Mandi. Her area of interest includes nonlinear dynamics and chaos, mathematical modeling, pattern and wave in ecology, epidemiology, mathematical biology, and differential equation. She has authored several papers in journals of international repute, such as Computer and Mathematics with Application. She holds various administrative responsibilities at IIT Mandi. We welcome you to our webinar, ma'am. Over to you.
Thank you. Thanks for such a nice introduction. Thank you for giving me a chance to share my research work with you all. Thanks, Professor Bhatnagar. So I'll share my slides here. Right. I think my slides are visible to everyone. All right. So this talk is about, yeah. So I have done some research on the current pandemic of COVID-19. So in this work, basically, we are modeling this current COVID-19 scenario, and we are trying to have a more generalized version of a mathematical model, which can help us to understand the progression of this COVID-19 disease at the same time for several countries. So here in this particular work, we have considered 4 different countries for this situation. So we are studying India, Brazil, Russia, and Peru. And we are trying to see if we can actually fit this mathematical model to these 4 countries at the same time or not. And can we use this for prediction of the disease? So as we are all aware that this disease started, the start of this pandemic happened in December 2019 from the Wuhan city of China. And thereafter, slowly and after certain time with a very fast pace, this disease went across the globe and in several countries at the same time. It also came to India. Yes, India recorded its first case on 30th of January in Kerala, and recently, September 2020, India started registering more than 90,000 new cases for COVID-19 almost every day. So, also in Brazil, the first case was reported in the month of February, on 25th February 2020. Similarly, in Peru, the first case was reported on 6th of March 2020. So we have seen that this pandemic spread across the globe. And so in order to understand this epidemic, or for that matter, any other epidemic, it is always very easier to understand it with the help of some mathematical model, because mathematical models can project how an epidemic progresses over time. And also it helps us to inform public health interventions. So in this particular work, we have tried to understand how this COVID-19 progresses with time. We have also tried to calculate the basic reproduction number for several countries using only one particular model. And basic reproduction number is actually very important quantification parameter for understanding any epidemic. Then we have tried to approximate the decline in this pandemic using this mathematical modeling approach, and we have also tried to understand the factors which might be responsible for decline of this pandemic. For that purpose, we have formulated a generalistic mathematical model, and our approach was if we can actually understand this particular disease for several countries at the same time. So far, there have been studies, but mostly if we look at the case studies, then a particular model has not been fit for more than one country. So this was something we tried to attempt in this particular work. So the mathematical model that we formulated for understanding COVID-19 is a compartmental model. So what is a compartmental model? Compartmental model is basically when we divide the entire population into mutually exclusive compartments. So here we have considered 5 different mutually exclusive compartments. We have divided the population N into a susceptible compartment. That is, it includes those population which can which are prone to getting the disease, although they are now healthy, currently healthy. The second compartment that is we have considered exposed compartment. This includes those individuals which have come in contact with the disease, however they don't have any symptoms. The third one is infected compartment. It includes those individuals who have come in contact or exposed to the disease and they are also showing symptoms in the disease, so symptoms of the disease. Next is isolated compartment L here. This includes those individuals who have come in, who have been exposed and thereafter they have been infected and now they are quarantined either at the hospital or at the home. And the last compartment is the removed compartment. So this includes those individuals which either been recovered from the disease. So the formative mathematics.
I request the participants to keep their mics on mute, please. I think somebody's mic is on. Aradhana, please check that. Just close everyone's mic. Sorry to interrupt, Dr. Neetu. Please go ahead.
No problem. Thank you. So the mathematical model takes the form as shown here in equation 1. So we can see that in the mathematical model can be very easy understand using a transition diagram. So here I draw the transition diagram for this model. So here we see that at a constant rate A, the population is being recruited to susceptible class, and from here mu is the death rate, natural death rate of the susceptible population. So mu is the natural death rate, and hence it has been kept same for all the 5 compartments. As it can be seen from these equations, mu S, mu V, that is the natural death rate of all the compartments. Then from susceptible population, a group of individuals move to the exposed class. So exposed class actually here beta is the rate at which the susceptible population comes in contact with the infected class and the isolated class, and then they move to those classes after interaction with them. So that is beta. Now lambda is the rate at which the susceptible population are coming in contact with the isolated class. So here we have made this assumption that even the individuals in the isolated class can infect the susceptible population. And how is it? How does that happen? Due to the movement of the healthcare providers and other facility providers, for example, if someone is providing food to them, and so on and so forth. So then this beta is coming to the exposed class, and also this exposed class population is moving to first the infected class and then to the isolated class. For that, we have assumed alpha 1 and alpha 2. Now, in the R, we have the population from, that is the recovered class. We have the individuals from all the 3 classes E, I, and L. And then there is a natural death rate of the recovered population. So this is the model that we have formulated. And if we move forward, so yeah, some of the parameters and its meaning I have already explained earlier is given here. So now what we have done to, in order to make this our mathematical study more easier, we have rescaled the model system, and the rescaled model system takes the form as shown here in equation 2. So we have obtained the disease-free equilibrium point, which is shown here as E0, that is N, and all the other compartments have 0 individuals. So disease-free equilibrium point is basically a point that we obtain from the model system, considering that there is no disease in the population. So once that this model has been proposed, we are setting this model under positive initial condition, knowing the fact that all the compartments include human population, and hence it has to be positive. And we are trying to first of all, in order to say that the mathematical model we have proposed, it is very important that it must satisfy all the basic mathematical properties that a model must should have. So for that purpose, we have here shown, we have checked whether it satisfies us with the basic properties or not. The first one is the positivity of the solution. So we have seen that the proposed model system, its solution SEILR at any time t is non-negative for all at all the time t greater than equal to 0 with a positive initial condition. So next property that we have checked is our solution that we obtain from the model system 2. It's bounded. So we have checked the boundedness by checking the supremum of the sum of all the solutions, which is we can see that it is bounded, and hence each of the class in the model is bounded as well. So basically, the model satisfies the basic properties in order to sustain as a mathematical model. So that we have already checked here. Next, we come to the basic reproduction number. So as I told in the beginning of this talk, that basic reproduction number is a very important quantification parameter in order to understand any disease, whether the disease will turn into an epidemic or not. So what is this basic reproduction number? It's the number of secondary cases or infections that will be produced by a typical infected individual during his or her entire life of infection or during his entire infectious period. That is your basic reproduction number. So, for example, if whenever the R naught is less than 1, so in that case, we can say that the what does it mean when we say that R naught is less than 1? This means that one infected individual will not infect less than 1 at a time. So in this case, there will not be an epidemic. Whenever R naught is greater than 1, for example, in this figure, so here this individual in the blue color is an infected individual, and the other individuals in the darker color, they are the susceptible population. So this one infected individual during his entire course of infectious period can infect 2 individuals. So here R naught is equal to 2. So whenever R naught is equal to 2, this means one infected individual is spreading the disease to 2 individuals from the susceptible class, and again these 2 individuals, each of them would be infecting the disease to 2 more. So this would mean that whenever R naught is greater than 1, in that case, chances of spreading the epidemic is high, or it will definitely happen. So we have calculated this basic reproduction number for the model system that we have formulated. So here the infected compartments are, we have considered only 3 compartments as infected, that is exposed, infected, and isolated. So these 3 compartments includes the infected compartment. Means we are assuming that these 3 compartments gives the order of transmission matrix F. So that's why this the order of this matrix is 3 cross 3. And transition matrix V is 3. Now here the progression from the exposed class to the infected class and further from infected to the isolated class are not considered to be new infections, but rather the progression of the infected individuals through the various compartments. So once we have obtained F and V, we obtain FV inverse, and we obtain FV inverse, and then by obtaining this matrix FV inverse, now we obtain its spectral radius. So the spectral radius obtained here is given like this, something like this, as shown here, and this actually gives us the basic reproduction number R naught, as given in equation 5. So this, as we can see, this value or this reproduction number is in terms of the parameters used in only in the terms of parameters used in the model. So it's much easier to calculate this now for real data. Now, next we have then further, once we have obtained, earlier we obtained the disease-free clear point. and then we obtain the reproduction number. Now we obtain here the endemic equilibrium point. So the state when the disease cannot be totally eliminated from the population is termed as an endemic equilibrium point. Now, for the disease to persist in the population, the exposed class, infected class, and the isolated class should not be simultaneously zero at the equilibrium state, which we consider in the disease-free case actually. So, with this clarification, we obtain the endemic equilibrium point as shown here. This is the value of E star. Further, we obtain the L star, R star, S star, and I star. So this gives us the endemic equilibrium point for the proposed model system. So this basically shows that there exists an endemic equilibrium point for the given model system. Now we check whether the equilibrium point that we have obtained is locally stable. If it is stable, then under what conditions it is stable. So we see here that the disease-free equilibrium point E0 of the model system is locally stable whenever the basic reproduction number is less than or equal to 1, and it becomes unstable when R0 is greater than 1. Also, we see that the disease-free equilibrium point is globally stable whenever R0 is less than or equal to 1. Now, backward bifurcation is one of the very important, again, this is, I would say, it's a very important quantification parameter to check whether how worse that a particular epidemic can be. So, whenever the backward bifurcation exists in the model system, this means the reoccurrence of the disease is here. Backward bifurcation in the disease transmission model is a phenomenon where a stable endemic equilibrium coexists with a stable disease-free equilibrium, and actually this increases the reoccurrence of the disease. So whenever, and it happens whenever the reproduction number is less than 1. Now the epidemiological consequences of backward bifurcation is that, as I mentioned, that is that the classical requirement of the reproduction number being less than 1 becomes only a necessary condition and not the sufficient condition for disease elimination whenever this backward bifurcation exists. So we have seen that in our model system, we have tried to calculate the condition for backward bifurcation. So for that purpose, we have used the basic reproduction number as given here. Now we have used this R0 to obtain these two parameters A and B as shown here. So sign of these two parameters A and B decides whether the backward bifurcation exists or not in the model system. So what we have seen that from the values of A and B for the proposed model system, it is seen that the coefficient of A remains negative and the coefficient B is positive. Hence, the backward bifurcation does not exist at R0 is equal to 1. Now we have used the real data for checking whether our model is actually fitting the real case scenario or not. So we have used this data for India, Brazil, Russia, and Peru from the WHO site, and we have used for simulations. We have used the MATLAB, and the data is used in the two different phases. The first phase is considered from 26th May to 10th July, and the second phase is considered from 11th July to 20th of August. So, using this data, we have, as I told in the beginning also, that one of the goals of this study is to estimate. So for that, for estimating the basic reproduction number, we have first estimated the various parameters involved in the model system. So the parameter beta, lambda, alpha 1, alpha 2, gamma, delta, and mu. All these parameters we have estimated for the case of these 4 different countries as shown here in this table. Further, we have also estimated the initial condition of the population. This means we have used this real data to find out what was the initial value of these compartments when we started our study, that is on 11th of July. So that we have shown in the second table here. Then further, we have estimated initial condition of the population for data available from 10 July to 20th of August, as shown in this first table. And we have estimated the parameter values for the data available again from 10 July to 20th August, as shown here in second table. So these are the parameters we have estimated, and now we use these estimated parameter values and the estimated initial population to see whether our model fits to the data or not. So here in this particular slide is for the case of India. So in the first figure, we can see that the blue line is actually the number of active infected population simulated from the proposed model system. And here the red dots, as it can be seen, that these red dots are from the data available on the WHO site. So this particular, we can see from this particular figure that our model fits for the case of India quite accurately for the duration of 26th of August. Again, it fits pretty well. So this actually shows that, and also we can see from the right hand side, the top for both these durations, and we see that the model, the residual is very low. It's not very high. So we see that the proposed model system is able to estimate the cases of infected population in the case of India accurately. Further, we have used this model to check that what can be the future course of this COVID-19 in the case of India. So we see that as per using also here, the blue line is actually the model simulation, so our prediction from the model, and the red line shows the official data recorded from the WHO site. So here we can see that the peak of this particular disease would lie somewhere in the September month, and this we are estimating that this COVID-19 pandemic may reduce or may become very, very minimal by the month of April next year. So, we have seen that the peak that we see here in the month of September is same as the current scenario, that we are seeing that the peak happened in the month of September, and now there is some decline in the new cases in the COVID-19 in India. Next, we use the same model, and we have tried to see whether this official data that is available on WHO site, whether our model can fit to it or not. So we have seen that there is it fits almost accurately, with a little bit of variation here between June, in the month of June, and similarly for the duration of July to August, we see that this is also fitting accurately. We also see that the residual calculation is not very, very big. So this confirms actually that the model actually fits the data accurately. So we have used this to predict the decline in the COVID-19 cases in Brazil, and we see that it might go beyond the 30th of April. So it might decline, but there will still be cases in the month of April next year. Then we have used our same model to see whether it can fit in the case of Russia or not. So in the first sub-period, it is fitting well, while in the second figure down there, left-hand side, we see that there is the fit is not that accurate. However, we can use this for prediction because the inaccuracy is very, very less, and also that is confirmed from the residual here shows that there is the accuracy, the fitting is almost accurate. So we have used this to predict the cases in Russia, and our estimation is that maybe by May next year, this disease may subside. Then next is the case of Peru. Here also we have fitted the operational data, and we see that our model fits quite accurately to the real data of the real active cases available in the laboratory site. And further, we have used this, and we can see that in the case of Peru, this might decline, but it might go beyond May next year. So we have further calculated the basic reproduction number, and we see that the basic reproduction number for the 4 different countries are shown in this particular table. So we can see that, as it was shown in the simulation as well, that in the case of Peru, it is going pretty long, even until up till May or beyond. So the basic reproduction number calculated here is quite high in both the phases. It is near about 2.4 and above, while in the case of India, Brazil, and Russia, it is coming around 1.4, 1.5, and 1.6. So basic reproduction number is actually giving us the how bad a pandemic can be in a particular country in a certain duration of time. So, basically, in this work, we have tried to understand how this COVID-19 would progress, and we have tried to fit one particular model to see if that model can be a more general model to understand the cases of different countries at one time. And we have, for this purpose, we have divided the entire duration into 2 different phases. And we have seen that our model actually is able to predict accurately, almost accurate, not predict, but I would say that more very accurately is able to fit the real data, and it can be used for understanding different factors which might impact the spread of the disease. So that is all. Thank you.
Thank you, ma'am. Thank you, Dr. Neetu Kumari, for a wonderful presentation on mathematical modeling and prediction of COVID-19. Moving ahead with the session, we have with us Dr. Kumudi Patil, Assistant Professor, School of Humanities and Social Science, IIT Kanpur, PhD in Industrial Design from IIT Powai. She's an assistant professor at Department of Humanities and Social Science. Prior to that, she was executive member of Board of International Toy Research Association from 2014 to 2017. I would also like to welcome Dr. P.S. Bhatnagar, Scientist E and Officer in Charge, Western Regional Center, Zoological Survey of India, Pune. He has done PhD in Eco-Behavioral Studies. I'm sorry. Dr. P.S. Bhatnagar has several publications and research paper, and he's also one of the coordinators for the webinar session. So over to you, sir. Dr. Bhatnagar, am I audible to you?
Yeah. I'm sharing the PPT.
Yes, sir.
You are seeing it on the screen?
Sir, it's
Can you see
loading.
it?
Yes,
Okay.
sir.
Just now is it there?
Yes, sir. So just full screen.
It is not full screen as yet.
No, it's not. No. No, sir.
Why? Otherwise, you try from your end.
Shall I try from my end once?
Yes, yes, better.
because we will be able to coordinate better.
Yeah.
Okay, I can't see the screen.
Ma'am, the presentation is loading, so
Yeah, Rana, you started to upload?
Okay, I think it's taking a little time from, I'm trying to upload, but it's taking a little time to take it. Could you share it? If it's faster from your end.
I think let Aradhana share it. Aradhana, can you do that?
yes, ma'am. Ma'am, just a few seconds.
Yeah, make it full screen. Okay, fine, thank you.
It's still
Yeah.
not on screen. Maybe the click button would do. The present button would do. That's on the right hand side too. Yeah.
Yeah.
Thank you.
Uh, yeah, Dr. Comedy, you would like to share the first, you would like to speak about the first slides?
Sure, certainly. So a very good morning to everybody. This is Kamadi Patil here and Dr. P.S. Bhatnagar. I'm from IIT Kanpur, and as introduced, Dr. Bhatnagar is from Zoological Survey of India. We are today going to present something on a topic on which the two of us have collaborated for some time and have been working on it. It's a work in progress. However, we had some findings and we thought that maybe it would be interesting for some of you to share your comments with us on how the work is progressing over. The idea is largely to look at what is our preparedness to battle a pandemic. And we tried to look into the notion of how good we are at fighting a pandemic on the basis of an index, that is the Human Development Index, which UNDP proposed. And our response is largely based on their comments on the comparison between Human Development Index and our preparedness for a pandemic. We are trying to illustrate the entire argument through infographics. So that is where the collaboration between me and Dr. Bhatnagar actually came over on too. So this is going to be a short session on what is it that we were able to analyze and infer from the data. Can we go on to the next slide, please? Thank you. This is a very interesting playground rhyme that Dr. Bhatnagar recently found. It is a rhyme that started off in 1918, which children used to sing in the playground and say, I had a little bird, its name was Enza. I opened the window and in flew Enza. So it's, of course, speaking about the Spanish flu and the influenza, which is more of a pun on the influenza, but it also speaks about how widespread the not just the awareness of the influenza was, but also about how much it had percolated into the culture of the people. Right? That is, in the everyday scenario, a rhyme had come into being just to speak about or sing about influenza. Next slide, please. Would you like to start here, Dr. Bhatnagar?
Yeah. So if we look at the chronology of epidemics and pandemics, so say pre-1900 and since 1900 also, then there is general reduction in interval. Say for example, for the last few years, the last pandemic was 2009, and prior to that it was the AIDS in 1981. So the 2009 was flu and 1981 was AIDS and HIV. And since for the last few years, say about decades or so, every 10 years, approximately every 10 years, we have an epidemic. Prior to that, if you look at before 1900, then before the Spanish flu, that is 1918, there were pandemics or epidemics not so frequently, and moreover, the disease spectrum was also not so wide as it is nowadays. The diseases were mainly restricted to plague and also this smallpox. Nowadays, we have all kind of diseases, and if we look at the challenges that we have before us, then there are many. The Spanish flu was more of a disease of the city. Now the COVID is also spreading to the rural areas, and then one more thing I would like to mention here is that the epidemics, we should all be very clear about it. I think it's not a very well-known fact that epidemics, pandemics, or in general, all the natural disasters, they have a natural cycle. It's nature's way to control population, and in terms of epidemics or diseases, it's a way to it is a way to control the genetic composition of the human society at large. So, as with the modern methods, we have devised a way to combat them, but at the same time, we have also observed that there is an anthropogenic acceleration, as I mentioned earlier, that every 10 years almost we have a pandemic now. And as per the Center for Disease Control, Atlanta in the USA, these diseases are only tip of the iceberg. We have many more waiting to happen. So this should be absolutely clear that these epidemics they occur or pandemics they occur naturally, but we have to keep the anthropogenic factors in check, and that is how we can reduce their devastation and also the disease spectrum. Then the other thing is that during the time of the Spanish flu, it was, as I said, the more of a disease of cities, and COVID is a more of disease is now also in these cities, but also spreading towards the rural areas. And another change that has happened since Spanish flu of 1918 is that we have an agency at the international level called WHO, which did not exist at that time. And this time we could isolate the virus very quickly. But in fact, it was already known that this kind of virus exists. in bats, but it took about 15 years for scientists to identify that this Spanish flu was caused by a virus when they exhumed bodies from later on in 1930s, and the virologists studied the virus from there. And as far as the vaccines are concerned, we had vaccines for smallpox, cholera, Asian flu, and of late, the Sputnik 5 with Russia is developed for COVID-19. These are the only vaccines against several epidemics and pandemics that have hit us. And one very important thing is that there has also been a change of nomenclature guidelines mediated by WHO, because when Spanish flu took place, Spain was not a party to the World War One, and so obviously the media was not regulated by the Spanish authority. It was not under the military control for military reasons. And in other countries, there was a media censorship due to the military reasons. So, as the Spanish royalty fell ill because of the Spanish this flu, so it got termed by media as the Spanish flu. So thereafter, when the WHO came into existence, it made the nomenclature rules that henceforth pandemics or epidemics will not be named after any region, because even if a disease may not have anything to do, it may bring adverse publicity to that region. And the ICT and commercial air transport was very less developed at the time, which is very more developed now. And obviously, there are other challenges that we have to take care of. Say, for example, this disease, the pandemic of COVID-19 has to be presented in media very rationally in terms of other mortality also, and as well as the social media will have to have some guidelines. In fact, some guidelines have been initiated because they were rumors, etc. And as our constitution has laid down the constitutional duty of every citizen to have a scientific temper and to treat other human beings with humility, so we should make good use of them to see what is right and what is wrong. So I think with this, I will hand over the next slide to Dr. Thomas.
Thank you so much, Dr. Bhatnagar. So, as I mentioned briefly at the introduction, we are basically looking at the comparison between the Human Development Index developed by UNDP and how they were trying to prepare the report way back in April 2020 about the preparedness of our countries in handling this epidemic. If you would like to explore this report more, I have given you a link below in case the link is, in case you want to see the entire report. Can we move on to the next slide, please? I'm sorry, can you go back? Okay, so for some reason the slide is not working, but okay, so what here I was actually trying to show you the data of the UNDP itself, where UNDP has tried to look at the Human Development Index and tried to mark out all the countries in the world on the basis of the index, and tried to argue that the countries with a lower ranking in the index are far more vulnerable to COVID than the countries with a higher index. And the reason why they came up with this conclusion is on the basis of several parameters. Some of them included health infrastructure, but there were also parameters related to poverty and also that of connectivity. So with all of this, they basically came up with, next slide, please, came up with the conclusion that in any country with higher HDI will have lower predicted vulnerability to COVID. Next slide, please. So we basically picked up their data and tried to map it over the current COVID scenario. So the current COVID scenario, we started working on this particular graphic a few days back. So it is the data that you're seeing about of the COVID cases is about a week old. If you look at this infographic, there are on the x-axis, you're basically looking at the countries, and at the y-axis, you're looking at the number of COVID cases. The bars, of course, are looking at the background. There are a few colors that you see, and the color coding is as follows. The dark green are countries with high HDI. The light green are countries with moderate HDI, and the cream or the yellow color, depending upon what your screen is showing, is low HDI. So now if you look at this entire pattern, you're looking at some countries which are closer towards my left, which is United States, South Africa, United Kingdom, Germany, Canada, etc., which are high on HDI, but their COVID cases are also, the number of COVID cases are also higher. If you go way down to my right, you will see countries like Chad and New Zealand, which is again a different country in terms of HDI, but also countries like Congo, which are very low in terms of HDI, but their number of cases is also very low. Next slide, please. So if you notice, all the countries which have been highlighted right now are countries which have less than 10,000 COVID cases. And I'm speaking about October right now. So it becomes fairly clear by this particular graph that Human Development Index as proposed by UNDP did not play an extremely important role in predicting our vulnerability to COVID. Next slide. But in this particular inference that we are drawing, there are a few exceptions. And the exceptions basically are Hong Kong, Iceland, New Zealand, and Liechtenstein. These four countries, these four countries seem to be countries which are very high on HDI, but at the same time, these are also countries which are very low in terms of their COVID cases. There are several reasons for this particular exception. Several of you may have even read about it. These have become almost case studies nowadays. And in these case studies, you would find the density of population, early detection, contact tracing, and social distancing measures which have been employed by these countries are largely the reasons because of which, despite the fact that they have high HDI and also high exposure to COVID cases, they have still been able to maintain or lower down their numbers. Dr. Bhatnagar, would you like to add something here?
Prevention is better than cure. In fact, in the last webinar we gave the case study of Lakshadweep. They took the control measures fairly early, sealing their borders very early, and had a very good control devices. So in India also we have an example, but of course these countries are also very good example. In fact, Hong Kong is so close to China and a heavy relationship in terms of travel and trade with China, but they have successfully controlled as far as the COVID is concerned. Yes, and New Zealand has also done very good because they could also fairly successfully control the number of COVID, and they are almost COVID-free now. Yes, please.
Yeah, Lakshadweep is a very good example from India, which Dr. Bhatnagar is talking about. Can we go on to the next slide? Thank you. We also, sorry, no, you moved a little faster before this. Previous slide, please. No, previous slide. Thank you. Just, in fact, one slide before this. Thank you, but just here. Okay. So, after we looked at the HDI and COVID cases data for our times, we also tried to go back and see whether there was any relationship between HDI and Spanish flu, which goes back late, very early to 1918. Of course, this posed a very huge problem, and the problem was that there was no Human Development Index way back in 1918, which I mean, this entire index is far closer to our times. Therefore, it was very difficult for us to basically say which one would actually go into high and which one would actually go to low. In fact, it was surprising to see that several countries which we today believe are high development or are on the high development index, for example, United States or Germany or Japan, were actually falling under the moderate HDI at that particular point of time. So because understanding HDI in 1918 was was a deal by itself. I would request Dr. Bhatnagar to give you an overview of how is it that data regarding HDI in 1918 was collected.
Yes, because as I said, all this data is based on UN as far as the COVID-19 is concerned. So prior at that time, there was no UN data available for the HDI. So we took the help of the historical HDI for the 1918 and even for 1918 that was not available. The earliest available data was for 1913 for most of the countries. So that we have taken up and utilized here to demonstrate for the HDI at the time of 1913. It goes back to actually slightly before the World War began, because during the wartime no database exists. So just prior to the World War I, we have taken 1913 data and we have assumed it to be true for the 1918. As far as the mortality data is concerned, actually Spanish flu is still a very big mystery, and it is not known how many killed exactly. The number is varying so much, but still we dig out some of the older studies and which had revised the earlier mortalities, and taking the mortality per thousand, we have calculated in terms of population of those respective countries at the time of 1918. So, or the closest to the 1918 census data, whichever was available, that was taken, and the number of mortalities for in terms of people for that country was calculated. So this is how the mortality was calculated.
Thank you so much, Dr. Bhatnagar. So coming back to the graph now, because I thought that it is important for us to know how HDI was calculated, considering that it was not present for 1918 at all. Now coming back to the graphic, as you noticed, the color coding remains the same in terms of HDI. Mortality rate and not the number of cases as we looked at in COVID. If you look at the mortality rate, United States seems to have had the highest mortality rate. Yeah? But this is a moderate HDI. And if you go ahead, this moderate HDI continues for a while till about Cameroon, and you have till about United Kingdom, and then from there on you're looking at countries which are low HDI but also seem to be having a higher mortality rate. Right? This trend continues on till the end, and the only two exceptions that you're looking at here is basically the two countries right in the end, which is Iceland and Liechtenstein again. These two countries, which are extremely high on HDI in 1918, are still showing a mortality number which is very low. Can you go on to the next slide, please? Okay. So if you notice the countries in the end, you're looking at less than 10,000 cases beginning from Ireland. Right? Ireland, New Zealand, Guinea, and all the countries below that till Iceland, Liechtenstein, are showing cases which is less than 10,000 cases. Now, this is a trend which seems to be slightly different from the COVID trend that you're looking at right now. That is, in the COVID trend, we saw that higher HDI also meant higher COVID cases. But in this particular case of Spanish flu, we are looking at moderate and low HDI and high Spanish flu cases. Can we move on to the next slide, please? Just like the previous case, we would also like to discuss the exceptions in this case. Iceland and Liechtenstein, as we said, are high HDI and low Spanish flu mortality. The reason is very, very simple. It is World War I going on, and these two countries did not participate. They remained neutral. Iceland, in fact, at that period of time was a part of Denmark. It was not even an independent country, but Denmark itself was neutral. Right? And Liechtenstein, of course, was also a neutral country. So Spanish flu is looking at a mortality rate which is extremely high compared to all epidemics that you're seeing. And the reason is not just because the flu virus itself was deadly, but you're looking at a combination of World War I and the flu. What it basically did was, if you think that in today's time, COVID has flared up or has spread far more because we have excess due to airplanes and ships, etc. Well, in in the case of 1918, though we did not have commercial aircrafts or we did not have so much of movement between civil population, but the army was moving. And because the army was moving, you're looking at a spread of the flu, which may not have happened if we were not in World War I. Move on to the next slide, please. And here I would like you to go back even further down from 1918 to 1855. There's a particular reason why we thought of introducing this particular case study of causes of mortality in the army in the East. This particular diagram which you're looking at is called a polar diagram, and it was developed by Florence Nightingale. Before I move on to the diagram itself, I think Dr. Bhatnagar can introduce Florence Nightingale in terms of a statistician to you a little, and then I'll go ahead with the connection between this diagram and Spanish flu.
As we know, she's called the lady with the lamp, and because of her work with the World War I prisoners, and she has also, it is very less known that she was a very good statistician, and she was a first lady member of the Royal Statistical Society, and later on she was given honorary membership of the American Statistical Society as well. She thought because the higher ups will not read the statistical report, so she used these pie diagram methods to present the data on the war victims and the diseases. This way she tried to convince the higher authorities easily about the need to set up more hospitals and more medical facilities, and also the fact that because the medical advancement was not much at that time, so she promoted this idea that preventive health measures and hygiene measures can be very, very important in promoting the health standards. And in fact, she has also done a lot of work in India, because of which the mortality in soldiers went down, and she firmly believed that if the health of the Indians in general goes up, then the health of the army in India will also go up. Okay, I will give it to you, Dr. Komali.
Thank you. So now what is the relationship between this diagram and the Spanish flu case that we're looking at? In Spanish flu, we are again trying to say that the mortality rate is very high because we are looking at a spread because of World War I. If you look at 1855, the period for which Florence Nightingale has made this polar diagram, you would find a very similar trend. So the blue wedge that you're looking at, but it's an old diagram, so you're not really looking at a blue, but the grayish, bluish color that you're looking at the wedge is the death due to preventable diseases. The red wedge that you're looking at, or the pink wedge that you're looking at, is death due to war. And black wedge is the one that you're looking at as death due to any other reason. Now, if you compare these wedges and the areas, you would realize that death due to preventable diseases is far higher than death due to war. So that is why we wanted to compare the Spanish flu and World War I to what happened in 1854. It is interesting that after looking at a polar diagram of this kind, the authorities were so convinced that Red Cross was formed after Nightingale's presentation of this particular data. Can we move on to the next slide, please? Okay. So we thought that we should now come back home from the world and see what is it that's happening in our neighborhood. In fact, not even our neighborhood, it's actually our home. So we looked at HDI data and COVID cases in India and tried to map that too. It came as a surprise to me that we don't have any low HDI states in our country. I was somehow, always under the impression that we must be having several states under low HDI. But according to the UNDP report, we do not have any state under low HDI. So we have only two, moderate and high HDI. The color coding remains the same. The dark green is high HDI and the light green is moderate HDI. If you look at our trend, you will see that moderate HDI seems to have gone fairly high to begin with. For example, Maharashtra seems to be topping, and the high HDI high HDI states seem to be coming right in the end. Right? For example, Lakshadweep, Daman and Diu. Lakshadweep, on which a case study has already been presented to you. Now, this seems to be a trend which is slightly opposed to the one which you're seeing in the rest of the world. That is, in the rest of the world, the low HDI countries seem to have come down, but in our case, it's the high HDI states which seem to have come down. But in this particular case, you will see something interesting. Can we go on to the next slide, please? Yeah. In our country, more than 75, it's actually 76.3% of the cases are found in the first 10 states that you see, beginning from Maharashtra to Telangana. So one is the entire issue with the HDI itself, but the other is also that some states seem to be concentrating or seem to be far more susceptible to COVID than other states seem to be. Now, Lakshadweep for you has been given as an answer because of the number of measures that it took. Were there other reasons because of which some other states may not have got as big a COVID patient or COVID cases? For example, Lakshadweep had a tourist population, but so did Goa. Goa is now flaring up. So is it that there are other reasons other than the HDI itself, which is basically causing this flare up in different states or in different states with different HDIs? Next slide, please. Click again. Thank you. If you look at the three graphs that we have presented, it basically shows that HDI is not the appropriate indicator for measuring the vulnerability of a population towards pandemic. Something that UNDP tried to do in April and doesn't seem to have worked for us. And I think the data is fairly clear in terms of how is it that it's not worked for us. Next, can you just click again? Though countries with high HDI had or at least was supposed to have a very good health infrastructure, for example, US, if you speak of health infrastructure, seems to be fairly good. Even though today we are hearing news that it is not sufficient enough for COVID. But the reason why the number might be going up, despite the fact that they have a good health infrastructure, is their connectivity. That is, what is their exposure to infected people? Dr. Bhatnagar had taken out some very interesting data on 30 countries in the world which had directly in contact with China, and US seems to be one of those. Okay. So connectivity through air travel and ships seem to have played a very important role in the spread of COVID and not so much of HDI. Higher the HDI, higher is the chance that you are exporting, importing, you are having trade, you are having other kind of cultural relationships with countries, because of which your exposure is far higher to other population. Next point, please. Can you click again, please? High HDI is also often associated with high density of population. And this is what Dr. Bhatnagar was speaking of when he said that Spanish flu was a disease related to urban areas. Why is he speaking of urban areas and not rural areas? That's largely because of density of population. High HDI speaks of high density. Delhi is high density. No wonder that the COVID infection is not only spreading easily, but it is also very difficult to contain. Next point, please. But on the other hand, if and when COVID reaches the low HDI countries, the mortality rate will be far higher than high HDI countries, because we have a poor health infrastructure, because these countries will also not be able to seal off their borders as well as other countries have been able to. They will not be able to do contact tracing as well as, let's say, the way Iceland did right in the beginning, or New Zealand was able to do. So they do not have the infrastructure nor the means to actually carry out a preventive measure if they get exposed to COVID. But then the initial part of the spread is whether they get exposed, and their exposure is very, very less. Yeah. Dr. Bhatnagar, would you like to add something to this?
Yes, actually, you have rightly said that we need to devise some new methods for the HDI. In fact, COVID cases have also been related to the PM 2.5 and PM 10 level. The these two particulate size matters in the atmospheric pollution. It has been found in some other countries that where these PM 2.5 and PM 10 levels are high, the COVID cases are also high because they affect the lungs adversely, and COVID is a disease of the lungs. COVID-19 is a disease of the lungs, and also the people's movement is to be regulated. Both the resident as well as the floating population density of the high density area, whether they are city areas, industrial areas, or tourist areas, that needs to be regulated, and we have to have measures of some screening and also better awareness among the people. Yes.
Next slide, please. So we would like to conclude with what Dr. Bhatnagar just said, that we propose that we are actually looking out for new parameters to be adopted in the HDI index to assess the vulnerability towards pandemics. And these parameters are not the developmental parameters that are currently in the index. Because pollution levels, connectivity, extent of informal sector. In India, the informal sector played a very big role in the spread of COVID. But informal sector is not present in the index. So is a pollution level, which is not present in the index. So an index needs to be made specifically for assessing the vulnerability to diseases or such kind of epidemics, especially now, given the fact that there seems to be a high possibility of such viruses to erupt more often. As Dr. Bhatnagar said, that ours is a century of viruses. We've just been on and off, and the frequency seems to be increasing more and more. So it's important that we are prepared with our data in order to understand how is it that we will be able to tackle the next epidemic if it hopefully it never comes, but it may. Next slide, please. Next slide, please. Okay, so sorry. Okay, no, the last one. No, the last slide. You're in the second slide.
Go back, Aradhana. Go back one slide.
Okay, so with this, we would basically like to thank all of you for listening to us. I'm sorry about the way we presented. There seems to have been a lot of delay in our slides, in the movement between our slides. But with, sorry, can you just remain on the slide? Yeah. So with this, we would like to end you with a rhyme, which was again sung in the playground in 1918. It says, obey the laws and wear the gauze. Protect your jaws from septic paws. Nothing has really changed from 1918 to 2020. The safety parameters are still the same. And in order to avoid a COVID, we still have to follow the same laws that were spoken of for influenza in 1918. So thanks a lot from me and Dr. Bhatnagar.
Okay, thank you very much. I do agree with what Dr. Komadi said, and it holds good even today, what was 100 years back. So, in fact, we should, when the epidemic or pandemic has taken place, then we are devising ways. We should be fully prepared for it, because as I said, the frequency is about 10 years or so. So that time we can utilize for R&D and other things, developing infrastructure. Thank you so much.
Thank you, sir. Pardon me, I was not able to introduce Dr. P.S. Bhatnagar earlier for the session, so do give me a chance again. So Dr. P.S. Bhatnagar has done PhD in eco-behavioral studies of mother-infant relation with special reference to wearing physical and behavioral development of infant in Ambag, Reserve Forest, Jaipur. Sir, we really thank you for a very insightful and very informative presentation. We would also like to thank Dr. Kumodi Patil. The presentation was very, very helpful, and the entire history of pandemics and epidemics was reflected on a very resourceful way. So we really thank you, ma'am and sir. Moving ahead with the session, I think we have reached to the question answer round, where the panelists can interact with the participants. So if any participants have any question, they can either raise hand or mention the question in the chat box, and the panelist will answer the questions.
System is in our country, which is unfortunately. So, if just see this slide, high slopes, they are part of road and bus.
Sir, your voice is not audible enough. If you can just, jot your question in the chat box, we'll be happy to put it across.
Nearest ditch and to the nearest stop. Each slopes as a part of the road person. And budget of course increase, but the maintenance.
If the participants wants to ask question, there is an option to raise their hand. So if they raise their hand, I will unmute them and then they can directly interact with us.
I think, Aradhna, we can just go for a formal close-up. I think we are not. Is there anything? No.
Not as such.
I can see there is one question for me. I can answer that.
Yes, ma'am, please.
Malati has asked that, tell us whether the model is applicable for state level analysis or not. So the answer to this is that yes, very much it's applicable even for state level analysis. What you have to do is that you will have to collect the data for the state and then you have to estimate the parameters. There is one question that I could read for me. Yeah.
Ma'am, shall I start with the valedictory session?
Yes, please.
Okay, yes, ma'am.
Yeah, Aradhna, go ahead.
Am I audible?
Yes,
you-
Aradhana.
Okay. So we have come to the end of the webinar session. Firstly, I would like to thank our Executive Director, Major General Manoj Kumar Bindal from NIDM. Sir has always guided us, always motivated us to conduct webinars. I would also like to thank our esteemed speakers for the session we had. Dr. Neetu Kumari, Associate Professor, Mathematics Department, IIT Mandi. Dr. Kumoti Patil, Assistant Professor, School of Humanities and Social Science, IIT Kanpur. And Dr. P.S. Bhatnagar, Scientist E and Officer in Charge, Zoological Survey of India, Pune. We thank the speakers for their wonderful and insightful presentation. I would also like to thank Dr. Sushma Guleria, who was coordinating the entire webinar. And last but not least, our participants for attending the webinar session with us. Our participants are our key audience, and we have always looked forward to them. Before I end this webinar on this note, I would like to give just two instructions. Firstly, regarding the e-certificate distribution, e-certificate will be awarded to those participants who have attended a total of webinar session of about 90 minutes or more, and who has also filled the feedback form. The feedback form will be mailed to all the participants after the end of the webinar, as well as the presentation will also be mailed to all the participants.
Aradhana, just a second. I think there's someone who has a question. Maybe
Oh, yes, ma'am.
Dr. Kumodini, I think if you can just help us out with this. So someone has asked, Khushbu has asked, if we can analyze, this HDI index for social and economic settings, especially in the rural context. Can we do this? And relating it to COVID.
Yes, so yes, it is certainly possible. The only slight hatchback that we might get there is at least in terms of India, the information regarding our rural sector is slightly less. But however, other countries seem to be having far better data. For example, US has very good data in terms of these parameters. However, yes, it's a very good suggestion. In fact, we must do it for our rural areas because though we are saying that it will spread not as quickly as urban areas, but we also know that once it spreads, it is an infection which is very hard to control. So yes, we must look into it, and it is possible. Maybe not to the same objectivity and not into the same precision as urban data, but yes, it's possible. I see there is, sorry. I see there is another question. Yeah, I see there is another question. It says, is pollution spreading COVID-19? Yes, this is something that Dr. Bhatnagar had said right in the end. He was speaking about particulate matter and the possibility of spreading of spread of COVID because of that. Yes, there have been several studies which basically speak of particulate matter and the spread of COVID. It has been well established now that it does, but yes, we have not been able to do much about it. For example, PM has been an issue in Delhi for really long, but you can't really control it as of now.
Yeah, I would like that answer by saying that COVID virus and CO2 has also been detected in sewage water, even in India also. And around 30 countries around in the world, they resort to wastewater epidemiology to monitor level of microbes and level of antibiotic use also. So monitoring is also important.
How do you, there's a question, I do not know who will be the best one to answer, but how do you see the impact of coronavirus on the unemployment, aspect impacting, and how that can be dealt with?
Yeah, actually, COVID-19 has effect differently on different sectors of economy. Say some sectors, say for example transport, say for example tourism, and say for example construction were very badly hit. But others, say for example e-commerce and e-trading and online teaching, and also the health sector in terms of telemedicine, they have been compensated to a large extent, And of course, COVID-19 will open up new employment avenues, new opportunities to work with, and some of the private companies have also have already resorted to work from home by distance measures, by tele measures, by e-measures. So COVID-19, it depends on us whether we use it as an opportunity or as a, as a curse.
Rightly said, sir, because that's what we otherwise also say, that every disaster provides you with an opportunity to look at the silver lining aspect. So you can look at it from a better developmental perspective as well. So maybe few
Yes.
changes in our strategies can help us out. Yes.
Yes. In fact, some countries like Oman, they come up with an app called COVIDpreneur, where entrepreneurs could start entrepreneurship using that app during the COVID time.
So it's a very difficult question to answer in some sense, because if you ask me, I have been fairly unaffected by COVID, in the sense that yes, I've had a lockdown and have had to sit inside. But if you ask me, I have not been affected financially at all because of COVID, and that's largely because of the very, very privileged position from which I come. I mean, I have a government job and I'm sitting quite tight and well off in my office right now. However, I think the impact that we're talking about of COVID is not so much of people who can access e-services and who have fat, nice jobs like mine. But I think the impact of COVID is seen in the informal sector the most. I, for example, work very closely with craftspeople, and I know hungry right now. They're starving largely because goods cannot be sold. They do not have access to e-services. The impact that is being looked at, I think there are several things to be spoken of, but one of them is that the informal sector needs to get upgraded in order to not lose the let's say the advantages of being informal. But however, it certainly needs to take on the advantages of the formal sector in terms of services, especially e-services. The second is that when it comes down to the informal sector, a situation like this had come down after World War I, when the Great Depression struck all the European countries largely. US started with what is called as the New Deal program. New Deal program is something very similar to what we would call as our Manrega. The only difference being that New Deal program not only dealt with daily wage workers, but New Deal program also dealt with, let's say, cultural people, for example, artists. Right? So it looked at everybody in the spectrum and tried to see to it that it gives employment for a particular number of days to everybody. When we say that we have to be prepared for the next epidemic, we don't have to be just prepared in terms of health. I think our country is a very good example of the fact that health alone is not going to ensure that the impact of COVID or any other pandemic is less. We have to look into other aspects, for example, employment, which is going to be obviously affected by an epidemic like this. So measures will have to be taken on those bases also before we say that the impact is there or not there. There is, of course, a silver lining when we say that, yes, new occupations or new opportunities will rise. But there are certain people who will never be able to take an opportunity, and that really comes down to our informal sector. If we can do something for that sector, then most probably the impact of something like a pandemic would be fairly restricted in a country at least like ours.
Yeah, I would like to add to Dr. Komedi's comment by saying that, like epidemics, pandemics, and other natural disasters, economic depression also has cycles. It comes in cycles. So COVID can be a very good opportunity to learn to deal with those cycles as well, to a large extent.
But like how Dr. Kumudini had put it, in NIDM we were working on this post-disaster needs assessment aspect, and as rightly said by ma'am, we were struggling with the very basic capturing of the complete informal sector itself. So for us, that itself became a challenge, to have that complete account of how large the informal sector is and all, and then to get into the the actual understanding and the statistical aspects. So I think there are challenges, but of course we'll have to look at the brighter side and then take things forward maybe. as a combined initiative. Thank you so much.
Thank you.
Thanks a lot. Thank you, everybody.
Thanks a lot. Thank you.
I would like to thank our speakers as well as our coordinators. Since I've already given vote of thanks, so it will be null in order to repeat it again. I'm sure I have made clear regarding the feedback and e-certificate. So once again, thank you to all our panelists for their time and consideration. And thank you to our participants for their patience and time. So on this note, I would like to end the webinar. Thank you.
Thank you, Aradhana, and everyone, please be safe, stay healthy. Bye-bye. Have a good day. Bye.
Right.